Hello students, we are going to discuss an experiment called half wave rectifier. Before we actually do the experiment, we will look into some theory about the experiment. The theory of this experiment consists of one, basic circuits discussion and little about diode characteristics and some details of graphical analysis and the waveforms associated with AC as well as the DC coming from the rectifier and some formulas and find the filters that will help us to remove the fluctuations in the final outcome in the form of AC that has to be rectified further, and we will be getting a better form of DC, and finally some applications of this particular experiment. The diagram you are seeing is the basic diode circuit. Of course, in this case we are giving a DC called the positive negative. A DC is positive is connected to the diode P type and N type is connected to a load resistor, and finally the negative is connected to the other end of the load resistor. This is a simple diode circuit. We will observe the earlier connection that we have seen is called a forward bias connection, and we will, when we take the readings of the voltage versus the current, we will plot the applied voltage on x axis and we will be getting the current and we will be plotting it on the y axis. We will observe until certain voltage there is no current that is coming. This is because it is going to overcome the junction potential of the diode. Further, as we increase the voltage on the diode, there will be increase in the current and it will be going to a value something like this. This gives us the idea of forward characteristics of the diode. Now, we are applying AC to the diode instead of the earlier DC. This is the basic circuit. The AC is connected to the P type and N type is connected to the load resistor other end is connected to the other end of the AC. The dynamic characteristics are those things when AC is applied, we will be getting the characteristic curve something like this. When voltage across the diode is varying, the current is also varying. Until that voltage called junction potential, there is no current available. The static characteristic is the first circuit that we were talking about, is the DC that is connected. The dynamic characteristic is the second circuit that we were talking about, is the AC circuit. The next visual that you are observing is the transfer characteristic. The transfer characteristic is Vi on x axis is plotted as the input voltage is varied, and Vo is the output voltage that you are getting is being utilized in the form of this characteristic, being the application of the AC is observed in this particular direction and the output is observed in this particular part. The AC part of this particular one is coming here as this, and the AC part of this particular one is not coming here. This is the characteristic of the diode. The diode in the forward bias is accepting the signal, in the reverse bias because of its very high amount of resistance, the signal is stopped and this part of the wave is being clipped and you will be not be observing any wave here and there is a gap here. The upper part of this wave, AC wave, will be coming again here, and like this we will have only upper parts coming in the output voltage. Here we can observe this T1 is one point and T2 is another point, T3 is a third point. All these 3 points when are translated on the right side, we will be observing T1, T2, T3 etc. all these are joined, we will be getting a curve like this. So, this method is called a graphical method. We will now see the details of the next basic circuit. This is 230 volts AC connected to a transformer. This is the primary and this is the secondary of the transformer. secondary transformer one end is connected to the p type of the diode and n type is connected to the load, and the lower end of the load is connected to the secondary other end. The voltage across this is VO that we were discussing in the earlier graphical analysis. This is the basic circuit. Now, the waveforms that we have earlier seen can also be observed in this way. This is about half wave rectifier, and we will observe the time or omega t is on x axis and the y axis is Vi. We will be observing the sinusoidal wave that is applied to the DC is in this form. This is the 0 of the sinusoidal wave, this is the pi, half of the cycle is over, next half of the cycle is inverted, and this is a complete cycle. So, here what we observe is, because it is an AC, alternating current or alternating voltage, there will be 50 times it will be fluctuating over this 0, and this part is 1/100th of a second, the remaining part is another 100th of a second. So, like this it continues, and when this is given to a diode circuit, as we have shown it earlier, we will be observing the diode circuit, the upper part of the wave, this part of the wave, half of the wave is accepted, because the forward bias of the diode is having low resistance, and consequently all entire signal is accepted. This lower part of the wave is not accepted, because it will become a reverse bias, as there will be large amount of resistance, and this will not accept the signal, it is being clipped or cut out. So, consequently we will find a gap here, and the signal continues for the next cycle, and so on. So, we will be observing these are the voltages and the corresponding currents. Whenever there is a load resistor, we will be observing the current in the circuit if we institute a ammeter. So, this current is being observed in the form of, this is upper part of the wave, lower part is again missing, upper part is coming. Now, we are observing a dotted line here. The dotted line here is a mean line between the maximum and the minimum. This is the maximum of the wave, this is the minimum of the wave. Whereas, in the upper curve, the maximum of this is this one, this is 0, and this is supposed to be minimum. So, it is equally spaced about 0. So, amount of DC that you observe here is 0, the amount of DC you observe here is more than 0, that will be some amount of positive DC, and we are observing this to be a mean line between the maximum and the minimum. So, this maximum is Vm and this is the minimum, this is about the first part of the curve. Next part of the wave is stopped, because it is reverse biased, and this is continuing like that. In the same way, we have, this is our DC voltage that we are observing. In the same way, we will be observing a DC current on this curve. This is a voltage curve, this is the current curve. We will be observing an AC voltage and a DC voltage. That means, when an AC is given through a rectifier, a diode, we will be getting both AC as well as DC. IDC is the amount of current, this is equal to Vm divided by pi into RL. This is equal to root 2 divided by pi into Vrms. We know that V maximum voltage of any pulse is equal to root 2 of Vrms divided by the RL will come as it is, and that will be, when we calculate, we will be getting 0.45 into Vrms divided by RL. Why are we interested in RMS? All the meters that are measuring the voltages RMS only. VDC is equal to Vm by pi, and this is equal to again root 2 by pi into Vrms, that will be equal to 0.45 into Vrms. Gamma is equal to RMS value of AC component divided by DC value of the wave. So, there will be a DC value and an AC value. This is defined as Vrms divided by Vdc, and then equivalent formula also is given by gamma is equal to square root of this brackets, and you will be getting I m by 2 divided by I m by pi whole square minus 1. This I m and I m will get cancelled. We will get pi square by 2 into 2 4 getting in this formula as root of pi square by 4 minus 1, and this will be giving us 1.21 is the value of this particular gamma for half wave rectifier. We will also have, because it is a rectifier, it will have the efficiency factor called eta. The eta efficiency factor is given as DC power delivered to the load, that is RL, divided by AC input power from transformer secondary. So, it is given as eta is equal to P, that is power at the DC divided by power of the AC. When we find out, finally it will come to 40.6 divided by 1 plus RF by RL percent. This is equal to very nearly 40.6%. This is called maximum efficiency. Now, we will observe the percentage voltage regulation, that is equal to V, that is voltage appearing without any load, minus the voltage appearing with full load divided by the voltage appearing with the full load multiplied by 100 will give us the percentage regulation, voltage regulation. Ultimately, for any application we require the percentage regulation of that particular rectifier. Now, we will also have the another definition, peak inverse voltage is the maximum voltage across the diode in the reverse direction. Now, we have got a pulsating wave that is coming in, because we have an AC as well as DC in the rectifier. Now, this pulsating AC is given to the filter. There are variety of filters, we will shortly discuss about that. This filter, the output of this filter is expected to be of this particular type. The output voltage, the with the time of the filtered one is supposed to be a straight line. The AC 230 volts is given to the primary, and this is secondary connected to a diode P type, and N type is connected to a capacitor, and this is again connected to a resistor called a load resistor, and the other part of the diode secondary of the transformer is connected to the capacitor, and this is connected to the load resistor. This is completing of the half wave rectifier with a capacitor filter. Now, this particular thing is connected to a capacitor, as we have seen in the earlier visual, in the form of a capacitor connected across the load resistor. We will find this is the value of the voltage increasing, the AC part of it, and it is not giving anything in the middle, lower part of the wave is stopped, and again upper part of the wave is continued. So, we will observe at this point it picks up and it goes to the maximum. Again after this point there will be this capacitor is, because it is able to store the electrical energy, it will in turn release that electrical energy when the diode is not conducting. So, this part is called diode conducting part, this part is called diode not conducting part. So, during that not conducting part there should be a DC coming, that DC is coming as a supply from the capacitance, and this will be again picking up, because diode conducting part will come here and it will make it to pick up to this part, and again there will be diode non conducting part taking it like this. Effectively, without this dotted curve we will be getting this the third curve showing in the form of load current with this is the load current with the time you will be observing there will be a voltage coming here and voltage is picking up during A dash and B dash, the diode is conducting, during B dash and C dash the capacitor, it has got already the charged value is being utilized for helping the circuit in conducting the current, and again C dash to D dash we will be able to observe that the diode conducts, and D dash again to this part will be continuing in the form of capacitance getting conducted. So, this shows the load voltage as well as this is the load current, how it is going varying. Voltage is plotted on y axis and an x axis, this is the time. We have got a detailed theoretical sketch of this diode current and the associated waveforms. So, this is the waveform AC is being given to the diode and this is the forward bias part of it. The reverse bias part of it is cut out and clipped off, again forward bias part of it is accepted. So, now we will have the effective voltage that is observed is starting from this point, the diode conducts and it will be increasing to a maximum value. This point is called cutout point. Cutout point is that point where you will observe the diode is disconnected effectively in the circuit, so that it does not conduct and the conduction is taken care of by the capacitance and it continues like this. The value of C and R put together is called a time constant. This time constant of the circuit will be usually large and that is compared to the distance between these two. The time taken for the reverse bias of this particular one is 1/100th of a second. This is very small compared to the time constant of the circuit and consequently, we will observe the capacitance take care of the conduction. Before capacitance, the charge on the capacitance goes down to a lower value, diode again starts conducting quickly and there will be cut in point. The cut in point is that one which makes the diode to start conducting and continues up to the cutout points. Between cut in point and cutout point, diode conducts, and between cutout point and cut in point the capacitance conducts. So, like this the conduction continues, we will observe a small amount of fluctuation in AC will be there compared to the earlier large amount of fluctuation. 9 volts part is connected to a p type of the half wave rectifier, that is diode, and the other end of the diode is now connected to a resistor straight away and this is called a load resistor, and resistor other end is connected to the 0 on this particular panel. This is the circuit completion and this circuit must give DC here and AC here. The connections between these two will help us the connections of the capacitance that is utilized for the measurement of AC. Now, first we will measure the DC part of it. We will, as far as measuring of DC is concerned, we have to take care of the positive of the meter as red one and that is connected here, this is the positive, and negative of the meter is connected here, this is the. You will be observing the meter is showing some value, the value is about 3.8 volts. The 3.8 volts has to be noted down as far as the calculation of gamma is concerned, and the AC value of the voltage can be measured by taking out these two probes and keep them in this particular one. We will turn this into the AC and what we will be measuring is AC voltage. Now, AC voltage when you look at it will be 4.8. Now, the AC value divided by DC value has been observed to be the gamma or the ripple factor. Now, this is the simplest of the half wave rectifier circuit. Now, the connections can be extended in such a way that we can have a capacitance connected to the output of this diode and connected to the electrolytic capacitor 1000 microfarad, and from the capacitor we will connect it to the resistor other end, that is called a load resistor. We will be connecting the capacitor as a filter. So, this what does it do? It filters out AC and we will be observing the AC value to be drastically reduced. Now, we will see the AC value is now coming down from 5 nearly to 0.7 volts. When we remove this capacitance, we will try to observe, show this again. Remove this, the capacitance, if it is removed and straight away connected to the resistor, we will observe AC value is high. And when we disconnect this and connect it here, we will be observing the AC value is getting reduced. That means, the ripple factor is getting reduced as far as with the help of a large amount of capacitance 1000 microfarads with the help of an electrolytic condenser, that will be reducing the voltage from 5 volts to 0.7 volts. So, by that way we will be reducing the gamma, that is which is the AC component variation. Now, with the help of with the capacitor in the circuit, that means with the filter circuit, we will be having the DC value connected in this, we will turn it into DC and we will be observing. Now, this value of the DC, now we will be measuring will be 9.2 volts, 9.2 volts is the DC, and value of the AC that you are observing is 0.7. So, 0.7 by 9.2 comes to a very low value compared to a without capacitance value. Now, straight away I am connecting the capacitance here, the without capacitance we will be connecting this one, AC rises and you will be observing the DC also gets reduced because of the no help of the conduction from the capacitor, and you will observe DC to be 3.8, and consequently the ripple factor gamma has been found to be 1.22 without the capacitance, and it will come down to a low value of about 0.072 with the capacitance. Now, we will go to the other connection in the form of a capacitance and another capacitance, both are connected and from diode to a capacitance and from capacitance to a inductance. This is an inductance, and from the inductance it is connected to the second capacitance, and from the second capacitance it is connected to the load resistance, and once the load resistance comes into the circuit, we will be observing the DC as well as AC now. So, this is DC, its value is sufficiently high, it has been found to be 8 volts nearly 7.9 volts, and when we go to AC it will be connected here through this capacitance. DC is blocked and we will be getting AC here, and we will be observing the effective value of this AC with the help of both the condensers as well as the inductance called pi filter. We will observe the pointer even hardly moves, there is any movement in this, that means it is effectively very small, it is beyond the capacity of this meter to measure the AC voltage. Consequently, we will observe the ripple factor is negligible with the help of two large capacitances of 1000 microfarads and a inductance. These three together it is called pi filter. So, what we have seen is earlier a single capacitance filter and now a pi filter with two capacitances and an inductance. The values of the gamma will be observed like this. We are coming to the final stage of the experiment. This is giving the details of the various circuits and the associated AC volts and DC volts and the ratio of AC volts by DC volts called gamma, the rectification factor. So, we will observe half wave rectifier, just half wave rectifier, just a diode. The value of the AC volts is 4.9, value of the DC volts is 4 volts, AC is more than this, and consequently the theoretical value of 1.22 volts gamma is appearing here. Half wave plus a capacitance filter. We know, we have seen the board, the capacitance is 1000 microfarads, has grossly brought down the AC voltage to 0.7 volts from 4.9 to 0.7, and the DC voltage is raised because of the storage of the energy in the capacitance 9.1 volts DC, and consequently the value of the gamma ripple factor has come down to 0.077. Half wave rectifier with L filter, the inductance as well as capacitance 2 are connected. Then the AC volts has come down still further from 0.7 to 0.3, and the DC volts is appearing is 0.6 volts, and the ratio is very important for us, that is the ripple factor has been found to be 0.050. Half wave rectifier with pi filter means both the capacitance are connected and the inductance is connected and the load resistor are there. The AC voltage is hardly any value, just 0.1, one small division on the AC scale of 10 volts. DC voltage has been found to be 7.8 volts, and the ratio of these two, that is the gamma, the ripple factor, is observed as 0.012. So, we will be observing the ripple factor coming down from high value to a very low value. That means, the AC component of the half wave rectifier is getting itself reduced and the DC component is getting itself strengthened, and the ripple factor is consequently very less. So, this is our result that we are observing. That means, this circuit behaves very nearly as a cell. That means, it gives the pure DC compared to the earlier AC and DC together.
ఈ మన ఉన్నత విద్యా కార్యక్రమాలపై మీ సందేహాలు, సలహాలు, సూచనలు పంపవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామిరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.